You're listening to the Corbett Report.
Welcome, friends. James Corbett here, CorbettReport.com, in a conversation that is being recorded on the 14th of March, 2017. And today we are talking once again to Dr. Judith Curry, the climatologist and former chair of the School of Earth and Atmospheric Sciences at Georgia Tech. And you will recall last year that we had a conversation with Dr. Curry about the Republic of Science, a very interesting conversation. Today we're going to be talking about a brand new report, a very comprehensive report that she has created for the GWPF that will be linked in the show notes. Climate Models for the Layman. Dr. Curry, thank you so much for taking the time to talk to us again today.
Well, my pleasure, James.
Well, I do want to get into the climate models for the layman, but before we do so, I suppose we should address the former chair of the School of Earth and Atmospheric Sciences, because since we last spoke, you are no longer associated with Georgia Tech. That is a very interesting story in and of itself. Perhaps you can let our listeners know a little bit about your decision to resign from your position.
Okay, well, I have been appointed emeritus professor, so I still do have a loose affiliation with Georgia Tech, but no salary and no responsibilities. I resigned my position after careful consideration over a number of years that I no longer wanted to be associated with academia, particularly in the climate field. The climate debate had gotten so acrimonious, and there was so much enforcement, if you will, of the politically correct viewpoint, if not the scientifically correct one, that it became uncomfortable, and I felt, that I could be much more effective by leaving academia and joining the private sector. So, and I want to make a point that this is no particular reflection on Georgia Tech, my institution, which I regard as better than most, but it was an endemic problem in the academic field surrounding climate change that I just didn't want to be a part of.
Well, very interesting. And for people who are interested in that in more depth, I will link them to your blog post where you announced that resignation, where you explain in some degree of detail that situation and make clear that it's not specifically about Georgia Tech per se. But let's move into this report, which, if you're known for being contentious in the realm of climatology, I suppose this will probably only contribute to that reputation, but in a good way, I would hope. It's called Climate Models for the Layman, and obviously it seeks to explore the topic of global climate modeling from a educated but non-technical perspective. So that's a very tall order. So let's attempt to reconstruct some of that in this conversation today. First, can you tell us what are global climate models, who constructs them, and for what purpose are they constructed?
Okay, global climate models are basically very complex, lengthy computer codes that are based fundamentally on physical equations, Newton's laws of motion, the laws of thermodynamics, things like that. And they're discretized in a sense where the globe, you can think about it as being divided up into little grid cells. They might be like 100 miles, 100 kilometers in horizontal dimension, and a few thousand meters to 1,000 meters in the vertical dimension. And the equations are integrated in a time-stepping method. It sounds simple enough, but the real complexity is what goes on within these little grid cells. This is where all the action is. This is where the clouds form, where the rain falls, where we have variations in vegetation and surface properties, topographic features, mountains and whatever. So there's a lot of stuff that is going on within each of these grid cells, and they're not based on these fundamental equations. They're what we call, they're parameterized. And these parameterizations, some have a sort of physical basis and some are just pure tuning. And so there's a lot of what I would call opportunities to get a bunch of different results in the climate model results, depending on the nature of these parameterizations and how the model is tuned. So that's the challenge in climate models. There's a lot of effort that goes into these what we call subgrid scale parameterizations, and this is from everything from clouds to sea ice to land surface and so forth. Climate models were originally developed, the kind that we see now, were developed around 1970 at that time, and they were designed to test our understanding of how we get the circulation patterns right. Could we produce the general climatological features? And scientists started testing the climate sensitivity to increasing carbon dioxide. What happens if we increase the output from the sun, and playing various games like that just to test the sensitivity of the models. And so these climate models were tremendously useful tools because they were able to, you could use them to conduct numerical experiments in ways that you couldn't do empirically with the real climate system. Okay, and we learned a lot from, these global climate models. And they, over the decades, they grew in complexity. Notably, they added chemistry in terms of atmospheric chemistry and ocean geochemistry related to air pollution, the carbon cycle, and things like that. Sea ice models and land surface models got more sophisticated. They reduced the horizontal resolution. And so the idea was that, the models should become increasingly closer to the truth in terms of simulations. Well, under the auspices of the IPCC, or the Intergovernmental Panel on Climate Change, there emerged an imperative for using climate models to project into the 21st, 22nd, and even 23rd centuries, the future of what might happen. And they were also used to try to understand past climates, including what caused the warming in the 21st century. So, and more recently, I would say in the last 5-ish years, they have really been used almost in a command and control mode in terms of setting emissions limits and, in terms of international climate and energy policy. So what we have now is policymakers, the public, accepting the outcomes of these climate models almost as gospel when they happen to be highly uncertain and don't include certain key things that are needed to make projections into the future. So that was what I was trying to point out, basically, in my report.
Well, it's interesting. Even you articulating the idea that these climate models are being used to at least tentatively project into the 23rd century makes a layman like myself laugh. It sounds so utterly implausible that we could have something resembling a climate model of the 23rd century based on a process like this. And again, from my layman's perspective, I see several layers of fuzziness going on here. For example, the resolution of these models, which I understand to be something that's somewhat limited by the computer processing power itself, that the increasing resolution requires exponentially greater processing power. But also things like the parameterizations, which is a difficult word to articulate, and the physical laws themselves that are at play here. So let's take a step back from this and say, okay, well, instead of looking forward, surely these models would be useful for looking backwards. If these are good models, then we can take a starting point from in the past and run them forward to our present time and see how they compare to the actual temperature record. And I understand this is something that does take place, hindcasting as it's called. And in your report, you quote a recent article in Science entitled "Climate Scientists Open Up Their Black Boxes to Scrutiny." And you quote, "Indeed, whether climate scientists like to admit it or not, nearly every model has been calibrated precisely to the 20th century climate records. Otherwise, it would have ended up in the trash." So what does this mean? What does this calibration or tuning of these models to the actual data mean? And what does that tell us about their reliability?
Okay. Models do need to be calibrated, so there's nothing wrong per se with this. The problem is when it's that there's explicit and implicit calibration. The explicit calibration is when you tune one of these parameters, okay, to a value that you think will give you the right answer. The implicit one is when you may have like 100 different choices, and you've run the models with all these different choices, and then you pick the one that matches your preconceived notions of what the outcome should look like. In the IPCC fourth assessment, it was rather astonishing that all the models agreed very well with the 20th century observed record. But then when you go into the 21st century, they diverge greatly. So then you ask, well, how did they agree in the 20th? So basically they all, calibrated it in different ways, but ended up getting the answer. And then when you integrate that forward into the 21st century, you get pretty different results.
Right. So just to make that explicit, there are many different models that could capture that data from the 20th century, but that doesn't mean that they are correct models and thus will not give us a correct prediction. Dr. Curry, are you there?
Those same simulations are used to determine how much of the recent warming was human-caused versus natural variability. And so because they don't get the phasing of the big ocean oscillations and circulations correct, any warming from the ocean oscillations is sort of implicitly inferred to be from carbon dioxide and human causes. So you end up, with that convolution in the 20th century simulations. So we're left without really knowing or understanding what's caused the warming in the 20th century. No one questions that humans have contributed something, but exactly how much we don't know, because it's a very convoluted, complex, nonlinear system. It's very hard to separate those things out. And we've been using the climate models, but the climate models have been calibrated and tuned in this unfortunate way. And so we're left, without an objective way to separate that out. And it may fundamentally be an ill-posed problem trying to figure out how to separate those things. But the way climate models tried to do it was they turn off the human forcing, the CO2 and pollution aerosols and things like that, and then just run the model in the 20th century to see what the natural variability would be. Then they add the human forcing back in, and then they look at the difference. But the problem with, both of them is they're not getting the multi-decaded to century to maybe even millennial ocean oscillations correct. So that's not really included. And there's still debate about, what the solar forcing was over the 20th century. There have been several reconstructions that disagree significantly with each other. So there's still a lot of uncertainty in terms of untangling and trying to understand how much humans have contributed to warming in the 20th century.
It seems to me that the central point of the current climate science debate is the quantification of equilibrium climate sensitivity. And that is, my understanding is that is ultimately what these global climate models are aiming at achieving, is a quantification of that. Can you tell us what is equilibrium climate sensitivity and what is our current best guess at it, or the IPCC's current best guess, which is different from its previous best guess?
Okay, if you double carbon dioxide and then you allow the climate to respond, which will warm, and it takes a number of centuries to reach equilibrium because the ocean response is slow, the amount of warming that you get at the end of a few centuries after doubling carbon dioxide is called the equilibrium climate sensitivity. For a long time, the best guess was that this was 3 degrees centigrade. Okay, so, and the IPCC gives a range. The current range that they give is between 1.5 and 4.5 degrees centigrade, and they give that with it's likely. So that's it. 66% chance that it's in that range. Now, the interesting thing is that in the most recent assessment report, they did not select a best value. Previous ones had said, it's 3 degrees. They did not select a best value because the climate models had an equilibrium climate sensitivity of about 3.5 degrees centigrade, whereas the observational methods, looking at the temperatures of the 20th century, gave much lower values, mostly below 2 degrees centigrade. So you had this sort of bimodal distribution of values, and they rightfully did not try to pick a best value because you had fundamentally two different solution methods that gave you two rather different variables. It's very hard to justify the higher values coming from the climate models based on the observations of the 20th century. And there's no way around that. And one of the rationales for the high values of equilibrium climate sensitivity is that the aerosol particles, these are little pollution particles, sulfates, black carbon that are in the air, they reflect the sunlight mostly, and this sort of counteracts the carbon dioxide. So you have a high carbon sensitivity that is partly counteracted by pollution cooling. Well, excuse me. In the fourth assessment report, it was assumed that the aerosol cooling was very large. In the fifth assessment report, they concluded that the aerosol forcing was much smaller, but the climate models had been working under the old values. And recent research has really narrowed this down, and that it is really much smaller than we thought. And then literally yesterday, I read a paper that blew my mind. I have to look at it more closely. But this was a team of atmospheric chemists, IPCC authors, and so on, that looked at the actual aerosol forcing from 1990 to 2015. And they said that it was actually contributing warming rather than cooling because of the dominance of black carbon that actually does have a warming effect. So this means that climate sensitivity to CO2 is even lower than we thought, because there's no longer this big cooling effect that counteracts, the high values of climate sensitivity. So this is a rather huge uncertainty. So, from this, I conclude that the real values of equilibrium climate sensitivity are on the low end of the IPCC values or even lower.
All right, so let's put this into perspective for people with the actual policy decisions that are being made right now. So again, the equilibrium climate sensitivity is now being estimated lower bound of 1.5 degrees Celsius.
Well, I think the lower bound should really be 1. So I think the real answer is somewhere between 1.
But in the fifth assessment report, it was 1.5 to, what was the upper bound?
4.5.
4.5. So, for example, the Paris Accord that we saw signed last year was aiming at a 2 degrees Celsius, or bounding the amount of warming to 2 degrees Celsius by the end of the century. However, they proposed to do that. Well, if equilibrium climate sensitivity is such that doubling leads to 1.5 degrees Celsius of warming, or even less, then all of that agreement would, I'm not sure what they'd even be aiming at that point. So this is not a trivial number. This is the central number around which trillions of dollars of decisions are being made right now. How can they justify that, given the incredible amount of uncertainty surrounding this number?
Okay, now here's another thing that to me is mind-blowing. Now, the IPCC has 3 working groups. The first working group is the physical climate system. This is where they come up with the equilibrium and stuff like that. The third working group is related to mitigation, the emissions scenarios and things like that. Now, so I already mentioned that in the recent IPCC assessment report, they couldn't pick a best value. But the third working group used 3 degrees in all its calculations. They were working on the old value from the 4th assessment report. So 3 degrees was wired into everything that group did. And all of the integrated assessment models, this is the ones that the economists use to calculate the social cost of carbon and the cost benefits, etc., they pretty much have 3 degrees hardwired into them. So they're all working from something that may be a factor of 2 too high. And this isn't really, being accounted for. I think the next generation of what's going on, will account for some of this uncertainty. But what we've been looking at so far in terms of this, it's assuming 3. The other issue is, what's your starting point? They say post-industrial. Well, in principle, that's like 1700 something. But the really big impact of humans on atmospheric CO2 didn't happen until post-World War II. So people have been sort of starting the countdown, say, in the late 19th century, 1880, something like that. So we've already seen about a degree of warming. So, but has that been bad? No, I think on net, our climate now is overall better, warmer, and nicer than it was when we were coming out of the little ice age of the 19th century. So whether we should, start from now or start from 1880 or 1750, I don't know. It's all arbitrary. So
I would love if someone could answer exactly what the temperature, the global average temperature should be. If someone could tell me what that number should be, that would be wonderful.
Okay, well now economists, this is interesting. I read a paper, and this is in the last month, that said, it was beneficial. This was better than what it was 100 years ago, and it would continue to be better until about 2030. So, maybe it is. To the extent that you believe these models at all, I don't know. But somebody did come to this conclusion, that maybe the early 20th century, is the best climate, not the 1700s or the 1800s, and that we should really start counting from the early 20th century. That would make sense to me, in which case we're a very long ways from reaching 2 degrees. The reason this 2 degrees is really rather arbitrary. Some German economists came up with this value, and then it got somehow accepted internationally. But the scientific justification is that if you look way back in geologic history, that they find a time when temperatures were 2 degrees warmer and the Greenland ice caps were gone. Okay, but then some recent research said, well, those temperatures were wrong. It was really the same temperature as now. And the ice caps aren't gone. So, that looking way far back, it's very difficult to get too precise about, what the temperatures were and what the causes were. And, it's tough. So personally, I tend to stick to the more historical record rather than trying to get too much out of the paleo record other than in a qualitative way. So the point is, maybe this is the best climate now. The extreme events, the extreme weather events are lower than they were in almost all regards than the 1930s and the 1950s, when they seem to have been worse. In China, I've read a recent paper where the extreme events, hailstorms, the whole works, had really declined since 1970. There were a few years when we had bad hurricanes and the insured damages were huge, but since then, we've seen a decline. So maybe this is a pretty benign climate that we're in right now.
Well, that sounds like heresy.
Yeah. But then people say, but sea level rise. Well, the sea level, we're coming out of an ice age. The sea level has been rising for 10,000 years. And it's a slow creep. If something catastrophic were to occur, like collapse of the West Antarctic ice sheet or something like that, then sea level could rise much more rapidly. It's happened before. It can happen again. But whether we're going to blame humans, carbon dioxide, there is a sea level rise problem. In some locations it's very bad, but the places where it's really bad, think New Orleans or Bangladesh, sea level rise is rising much faster than anything that could be explained by warming. And we're seeing, land subsidence, groundwater withdrawal, lots of other factors that go into these rapid rates of local sea level rise. So, I think if we figure out how to manage a slow creep of sea level rise and then accept that the current climate is actually pretty nice, and then, we don't want to do long-term harm to the climate and the environment, but it does sort of, if climate sensitivity is low, and if the economists are right that the current climate is pretty nice, it sure does remove a lot of the urgency for rapidly transitioning away from fossil fuels as our energy source.
Well, spending trillions of dollars and fundamentally changing the nature of human civilization as we know it does seem a bit drastic based on these climate models, which, again, I think you demonstrate quite well, have some uncertainties. I want to direct people once again to the report itself because obviously there's a lot more detail in there. But before we go, I want to re-stress the point that this is not to say that there is no use whatsoever in climate modeling. It's just that the uses that these models are being put to is highly questionable. And you have a great quotation from statistician George Box in this report. All models are wrong, but some are useful. That's a very interesting and profound statement. Perhaps you can tell us, what could these climate models be useful for if it's not for predicting the weather in the 23rd century?
Well, they're useful for, again, their original role was to understand the climate system. And, they remain useful for that. They would be more useful for that if we were spending our efforts developing new structural forms for the models so we could explore different things rather than focused on the goal for IPCC, which is related to human-caused climate change. So I think we would make better progress in understanding the climate system if we were unleashed from that particular responsibility and could explore different model structural forms so we could really increase our understanding and try to figure all this out.
All right. Well, I think we'll have to wrap this conversation up there. I do thank you for taking the time to do this, but before we go, perhaps we can direct people to your website and or any other places you'd like to direct them to.
Okay. My blog is judithcurry.com, and my company, the website is CFAN climate.net. I encourage you to check out both sites. And at my blog, come join in the conversation.
All right, very good. Well, we've had a couple of breakups in the conversation, but we were able to hear most of what you said. So thank you again for taking the time. I do appreciate it. Dr. Curry, I hope to talk to you again in the future.
Okay, thank you, James.
The Corbett Report is brought to you by you. Your support makes the Corbett Report possible. Sign up for the subscriber newsletter or purchase a DVD at corbettreport.com/support.
I'm looking. You can give me a second. The sun is rising. I need to close the blinds. Sorry.
What an appropriate interruption.
Yeah, the sun is rising.